Okay, so I'm going to talk about some work that I've been doing with one of my students. This is not his main research, but he very kindly has been helping out with this project. And this has really it's sort of been one of my, you know, so unlike Dave, I'm happy to keep the language as it is and just focus on trying to make it run faster. And so a lot of what I've been doing over the last few years has been focused on making it run faster. And this is an example of that. So I'd like to start with just a little motivation. So we all know ML is a safe language. And when we talk about that, usually what we mean is this great slogan that well-typed programs don't go wrong. But it's safe in another way, which you could argue is maybe the same way, and that is that mechanisms like subscripting an array or a string or a vector, or adding two numbers where the result is not representable in the size of the machine word, those undefined operations get mapped into exceptions. And that means that compilers have to implement, and libraries have to implement checking code that detects whether those situations occur, and rather than doing something undefined, actually generate exceptions. And of course, this causes overhead, and many other languages have this issue as well. I mean, Java is perhaps one of the most widely used examples of that. Of course, new dynamic languages, et cetera, as well. So as a compiler writer, one wants to try to fix this, and I'm not the first person to address this. In fact, you can go back to a paper written by Mark Stein et al. In 1982, which tackled this issue, I think in the context of Fortran, but I'm not 100% sure that's the right language. And in fact, even earlier, Harrison, more from the perspective of just trying to optimize conditional tests inside programs. So this wasn't really about range bounds checking or anything. It was just really more about just the observation that there were lots of conditionals inside programs, and if we could optimize those at the compile time, we could make the programs run faster. And so he looked at range analysis in the 70s. And when Java came along, this whole topic got a real big boost. And there was a paper by Ross Bodick and co-authors, which has introduced some important ideas about how to solve this problem. And perhaps one of the more important ones was this notion of extended SSA. And I'll talk a bit more about what that means in a moment. And that particular paper was looking at essentially the range tests, and it did this in terms of building up a constraint, what are called difference constraints, which is an idea that Von Pratt had introduced eons ago, I think, again in the 1970s, if I remember correctly. And then there's some other work that Sue and Wagner did, where they, rather than looking at it in terms of scalar variables, they look at it in terms of intervals. And they came up with a way that you could solve these interval constraints in cubic time. And lots of people have built on that basic framework of intervals, including the stuff that I'll be talking about. So we're stealing from all of these previous people. So we use the idea of extended SSA, but we do that in the CPS setting. We use an interval language that's very much like the Sue Wagner language, and then we use a solver that's based on some more recent work by Rodriguez et al. And I should mention that really, if you read these papers, at the end of the day, it's the Cousteaus who came up with the basic ideas about how to do this kind of analysis, and everyone else has just been standing on their shoulders. Okay. So CPS. So this is a sort of a fragment of the intermediate representation that the SML New Jersey compiler uses, extended with these pi things. there. And the idea of these pi bindings is that they provide a mechanism to rename variables along splits in the control flow graph. So if you know SSA, right, you have phi nodes which provide a way to rename variables at points where control flow joins. And this is sort of the flip of that, where we want to have a way to rename variables at places where control flow diverges. And it's, Bodick called this stuff extended SSA. There was also, around the same time, something called SSI was introduced. And you can actually even go back further to one of my former fellow graduate students at Cornell, who worked with Keshav Pengali, and they actually had an intermediate representation that in fact had exactly the same ideas in it. That was, I forget what it was called though. But the key thing about this renaming is it allows you to encode the flow sensitivity into the variable names, okay? And so what that means is that once you've done that encoding, you don't actually have to think about the control flow anymore. You can just think about the relationships between the variables. And so it gives what the data flow community calls a sparse analysis, and it's a really big win, because once you've got the constraints on the variables, the control flow just doesn't matter anymore. Okay, so there's a bunch of notation we'll have to go through. I may go too quickly, so please ask questions. So we start with this idea of bounds, and basically bounds are just integers, and we extend the integers with a bottom and top element with negative and positive infinity. And it's also, because we're working in the world of machine hardware, and we typically have finite precision integers as our default integer type. Most ML compilers do this. So I'm going to use L and U to represent the range of the least and maximum integer for some type. And in standard ML, we actually have multiple precisions, and so you would actually have to have multiple L's and U's for different types. But for now, let's just imagine we have, say, like 64-bit integers, and so L is minus 2 to the 63. And these bounds, of course, are ordered by the standard operation of ordering integers, and you can define the minimum operation and join operations. So min is the meet. Join is the join. Sorry, join is the max. You can also think about operations like addition and negation, and so from negation get subtraction on these things. But addition is a partial function because it's undefined what adding negative and positive infinity together are. Okay. So from bounds, you can then define intervals. And intervals can be empty, or they can consist of a lower bound and an upper bound. And by convention, we'll assume that the empty element is just has lower bound of positive infinity and upper bound of negative infinity. But in fact, it's useful to specify that if you construct a concrete, if you construct an interval where the lower bound is greater than the upper bound, that's the empty interval. We also have this notation, so I down arrow is the lower bound, I up arrow is the upper bound. So the intervals form a lattice as well, and we can order it by subset. So if you can think of intervals as just sets of integers. And you have the usual operations. We can also extend the notions of addition and negation to intervals as well. So this gives us a vocabulary that lets us write expressions involving intervals. And we need to add one more thing, which is abstract bounds. So these are basically just symbolic representations of stuff that we care about, but we don't know. So in particular, one of the things we care about a lot is the length of arrays. And so if A is an array, we're going to write, I sub, excuse me, absolute value or norm, whatever you want to call that, of A, and that's just the singleton interval, which is the length of A. But of course, we don't actually know where that lives in the space of intervals. It's just we know it happens to have that rough shape. And then also we'll use the notation of I sub x to represent the range of a variable x. And the key thing here, going back to the extended CPS stuff, is that, variables, of course, are bound. They're not mutable because we're functional programmers. And we're going to have different names for variables and the different control flow branches, and thus the interval expression for a variable does not change based on control flow, because when we go from, we have like x, and then we say something like if x less than y, when we're in the true branch, we're going to have a different x. We're going to have x sub t, which is the true version of x. And in the false branch, we're going to have x sub f, which is the false version of x. And those are different variables, and thus they will have different interval expressions. And so that makes everything work very nicely. So then we have this form of constraints, and again, this is just taken from the Su and Wagner formulation. So you have some sort of constraint expression, and then you can intersect it with a concrete interval, so not an interval that doesn't involve any of these abstract things, but has concrete bounds. And then we can say that that's in the subset of the interval for x. And basically that's just that represents the flow of information, right? The stuff on the left is what we've defining in terms of computation, and that's going to flow into the definition of x. And very frequently I is just going to be top, so we will omit it in those cases. Okay, so that's the basic framework of how we want to write constraints. And let's consider some program forms. So the first one is, let x be the length of A. And that introduces a constraint that basically just says that x is the length of A. If we have a trapping arithmetic operation, so trapping add here, so the T here means that if x plus y is out of range, not representable, then we're going to get some sort of trap raised, and so this instruction will not complete, right? So we take I sub y plus I sub z. That's the result of adding y and z together, and that interval might be bigger than the LU interval, right? It might extend past the LU interval in some way, and that would be a trapping situation. But if this instruction completes and x gets a value, we know it's going to be in the LU range, and so that's why we have the intersection with LU. So either this instruction fails if I, y, and I plus, if the x and if y and z are out of, their addition is out of range, or else it succeeds, and if it succeeds, it's going to be in the LU interval. But hopefully we'll have better information than that. And then conditionals are the most interesting case. So we have a conditional, say like x less than y, and we rename the variables x and y in the two branches, and we only need to rename the variables that are actually tested, because nothing else, we've learned nothing else about any of the other variables. And so in the true branch, we're going to be able to say, well, the interval of x, and so this is the interval of x above the if, intersected with the range from the least integer up to the top of the interval of y, the upper bound of the interval of y minus 1, that should be less than or equal to, or sorry, subset of the interval for xt. And we get a similar kind of expression for the interval for yt. And that's just basically expressing the information that you learn from that particular conditional in the true case, and then there's a similar thing in the false case. And I should say that in the original version of the paper, and in fact in the literature for this problem, typically people only care about the true branch, and so often use a much simpler version, just essentially saying Ix flows to Ixf and Iy flows to Iyf, which those are sound constraints, but they're not as precise as you can be. So I've actually revised the paper this morning, I think. So if you follow the link, have followed the link previously, you may want to follow it again. But to have the more precise version of these. How are we doing? Okay, so the other place where you have to worry about generating constraints has to do with joins. And in CPS, joins are just lambdas or functions. And we can use a flow analysis to approximate the set of call sites that call a particular function definition. Now, in standard ML of New Jersey, the flow analysis is what we might call a first order or syntactic flow analysis, which is basically the situation where f and g are the same name, the same variable. But you can imagine you might be using something like 0CFA and get much better information, and this framework would certainly let you use that better information if you had it. So if you know that there's a particular call site G that flows to this function, then we can write that yi, so the ith, oops, sorry, the variables of the function should be x's, so that's a typo. So that we can write yi flows to xi. So where xi is the parameter, and again, should be in the function binding, and yi is an argument which comes from the call site G. Now, normally what we do here is we say, well, if we know all of the call sites of a function, then we call the function a known function, and we can do something interesting there. But if there might be a call site that we don't know about, because we're not doing whole program analysis here, we're doing module level analysis, and so maybe the function gets put into a data structure, or maybe the function gets passed as an argument to some external function or something like that. So if we don't know, then it's an escaping function. And the other thing is we're only really interested in variables that have integer type. Because that's the only thing we're analyzing. So we can avoid worrying about most of the variables in the program. But if we know all the call sites, then we can just basically take the union over the, so for every y that's a parameter that flows to the ith variable, assuming the ith variable is an integer variable, we will include the interval of y. So we'll just get a big union of all of those intervals, and those all flow to xi. And if it's an escaping function, we're going to have to add LU, but once we add LU, that's just going to wipe out all the other information we know, so we just put LU in there. Okay, so that's basically how we generate constraints, and once we've generated constraints, we have to solve them. And so the basic way you do this is that what we want to compute is what's called evaluation, and that's just basically a function row that maps variables, and technically these are the eCPS variables. So it maps those variables to intervals, and it has to be consistent with the constraints. There's obviously a trivial solution, which you could just say everything is top. It's not a very interesting one, but okay. So one of the sort of challenges of our approach, and this is something that's not covered in most of the literature, but some of the literature, is that we have symbolic intervals, right? We have these intervals that correspond to lengths of things. So the work by Bodick and co. had that idea, but the Wagner paper just worries about concrete intervals. So we do know some things, which and it turns out that this allows us to solve, to answer most of the queries we need to answer. So we know that the interval for a length interval is going to be in the range from 0 to m, where m is the maximum supported array length. So that might be 2 to the 63 minus 1, or it might be something smaller than that. But whatever that number is, you can always conservatively replace one of these length intervals with that concrete interval as an over approximation. So the goal is to compute rho, and our approach is based on the algorithm that's in this paper by Rodriguez et al. From 2013, and the basic idea. So all of I think pretty much all of the papers that we looked at in this sort of general area of the literature use a hypergraph to represent the constraint system. And the reason it's a hypergraph is because the edges correspond to constraints and the nodes correspond to variables, but a given constraint can have multiple inputs, and therefore you get a hypergraph. And one of the key tricks for performance tricks that people have come up with is this idea of first computing the strongly connected components of this graph. And in C programs, which is the Rodriguez paper is actually about analyzing C programs. For C programs, you have you typically the size of the largest strongly connected component is typically orders of magnitude smaller than the size of the whole graph. So they give an example where the largest, for one of the benchmarks they use, where the largest strongly connected component had like 1,000 nodes in it, the graph had 1,000,000 nodes in it. So by solving these things in topological order, as each solution is computed, that populates the evaluation for all the variables in that part, and those are the variables that are you'll need later on for as you process things in topological order. So if you have a non-recursive component, which turns out to be lots of the components, maybe a majority of the components, solving the constraints is trivial. It's just really applying the valuation you have to the variables on the left-hand side of the constraint, and that determines the value on the right-hand side of the constraint. For recursive components, we use an iterative process that involves widening to basically deal with the fact that otherwise you could get this sort of unbounded growth, and then narrowing to refine the bounds so that you actually get useful information out of it. And this is a fairly standard but an old idea, and the details are in the paper. The paper, my student wrote a very nice little description of exactly how all that stuff works. And so, okay. So once we have this valuation, we can actually use it, which is the goal of all this work. So given rho, if you have a trapping addition, you can weaken it to a non-trapping addition. If rho of the interval expression that describes the result of that addition is contained within the range of representable values. If you have a conditional, x less than y, we can replace that with a true branch if rho of the upper bound, rho of ix upper bound is less than rho of the y's lower bound, right? So that means that the interval, the possible values of x have to be less than all the possible values of y, and therefore this is going to always be true. You can also figure out the false case in a sort of similar argument. Now, the paper talks about unsigned comparisons. So this is I had a chat with Fritz Heinlein the other day about this, and it was sort of realized that this is maybe not something that people know well. So it's a trick, but it's a great trick, which is that because of 2's complement arithmetic, you can do a comparison test between 0 and n by doing it as an unsigned comparison. Because if the variable, say I, is negative, it's going to be bigger than a positive n, right? Because n is, if the high bit is going to be 1. And if we do an unsigned comparison, we treat that as just a very large positive number, right? And so therefore, because of that trick, compiler writers should implement subscript tests using unsigned comparisons rather than signed comparisons, because it means you only have to do 1 comparison instead of 2, and that happens to be the constraint you need to solve for that. And that is the constraint you need for that, and I'm almost done. Yeah. So we've implemented this analysis in the 2025.2 version of SML New Jersey. So this is the version that uses LLVM as its code generation infrastructure. I would say that they're still chasing down bugs, so I don't have a good performance analysis for you, but we have been able to run some things, and in particular the example in the paper, if we run it, which is just basically add up the elements of an array of integers. So this is kind of like represents the best possible speed up you could get, because it's the conditional tests dominate the code. We actually see a 57% speed up there on adding 250,000 element arrays. Obviously the speed up for bigger programs is going to be a lot worse. I would mention that there are other opportunities for optimization. So standard ML has trapping coercions. When you go from, like, say, a big integer to a small integer, you have to test whether the big integer will actually fit inside the small integer, and if it doesn't, that's causing an overflow exception. But again, that's something that range analysis might, in fact, be able to tell you is not going to happen, and you could get rid of that test. It's also conceivable that big num arithmetic could be optimized, where you could tell that you could actually get away with fixed sized arithmetic because the results are going to be small enough. And with that, I'm happy to answer any questions.
Yes, we do have time for 1 or 2 quick questions if folks have them. Looks like Martin does.
Great. So it seems your analysis is kind of sensitive to the propagation, to the conditionals appearing directly in or the test appearing directly in the conditionals. So, for instance, if you bind first a variable b to whether something is less than something else, then you lose precision.
Yes, that's true, although the optimizer, we run this after we've done a lot of sort of standard optimization, so in that case it's very likely that the test would have kind of migrated. Well, there are 2 things. One is, and this is something we haven't experimented with, but conceivably we could run this more than once. And so it's conceivable, like just the way, say, contraction works well if you do it more than once.
You have the built-in order type in standard. So do you do something special with that, or?
Order is something that we currently don't have built into the compiler. The compiler doesn't know anything about order. It's just a data type. So that limits some of the kinds of optimizations we could do, and that's something that I think, for other reasons, would be good to make the compiler aware of. It's
This might be too broad of a question, but I'm just curious if you have any examples of kind of bounds checks where this sort of analysis succeeds that more kind of naive approaches don't.
Yes. One of the things I experimented with, and again, this is, a more detailed performance study, I did this comparison, was just using essentially a kind of redundant range check optimization, because it's very frequently the case that you'll have a test and then you'll have another test that dominates,
Right.
where the first one dominates the
Right,
second
right,
one,
right.
right? But one of the problems is, and one of the things that this analysis does very nicely is it deals with the fact that you have a mix of signed and unsigned comparisons. And that's actually a little bit harder to reason about, because the unsigned comparisons are, are doing two things at once.
Yeah.
And it's also the case that I haven't figured out a way to do that for the trapping arithmetic optimization. So,
Thank you.
Let's thank John again for a fun talk.